For almost every laboratory, solution preparation is a basic task. Nevertheless, it's an important step. Results depend on the precision of this. Any change in concentration, pH, or any other change can interfere with the data obtained at every experiment, especially in laboratories as delicate as a microbiology laboratory or this, a genetic engineering laboratory. In this practice, different solutions that will be needed at future practice were made to remember the correct way to prepare it and to ensure the precision of them.
A solution is a homogeneous mixture that is formed from the combination of two or more substances, known as solute and solvent. The solute is the substance that is found in the least amount, that which is dissolved in the mixture. Meanwhile, the solvent is the substance that is found in greater quantity, that in which the solute dissolves. In order to prepare a solution, it is necessary to dissolve a certain amount of solute in the solvent. However, it is important to take into account the solubility of said solvent, since it will determine if the solution is saturated, unsaturated, or supersaturated. According to this, we can have a saturated solution when you can no longer dissolve any more solute in a specific volume at a specific particular temperature. An unsaturated solution is obtained when you dissolve less amount of solute than the limit that can be dissolved in the solvent. A supersaturated solution is the one that contains more solute than the limit that can be dissolved in the solvent at a determined temperature. These kind of solutions are unstable and can be obtained generally by heating, rapid cooling, or sudden decompression.
Concentration can be defined as the amount of solute and solvent in a solution. For this purpose, it exists different units. Each of them depends on how the amount or concentration is measured. First, when the concentration is expressed in moles of solute per liter of solution is called molarity, or represented as the word M. Second, molarity. That represents the number of moles of solute dissolved in 1 kilogram of solvent and can be represented as M. This specific type of units is used mostly for boiling point elevation and freezing point depression. Third, percent by mass and one of the most basics. It represents the mass of solute divided by the mass of solution per 100. Last, parts per thousand, per million, per billion, as the concentration needs. For example, parts per million is commonly used for environmental studies. Parts per thousand indicates how many grams there is for 100 grams of solvent. Same idea for million and billion. A correct technique to prepare solution is first, make the necessary calculation to obtain the concentration that is required. Next, measure the quantity calculated of solute or solutes. Then, fill half of the volume of solvent in the container. Next step is to pour the solute or solutes in the container and, if it is necessary, rinse the container for avoid losing part of the solute. Then, stir the solution until the mix looks homogeneous. Finally, fill the volumetric container to the wanted volume. After preparing a solution, it is necessary to verify the concentration of it to be sure that this solution will work as we want. There are different methods. There is the experimental or chemical and the analytical method. One of the experimental methods is the titration using indicators. And an example of an analytical method is spectrometry.
For the preparation of solutions and culture medium, it is necessary to identify the GHS classification of each of the reagents to be used: toxicity, flammability, corrosivity, health damage, cares, and protective equipment. Investigate the density and molecular weight of the reagents. Activity 1 and 2. Investigate the procedure to carry out each of the solution and culture medium. Identify if the solution in the sterilization process pH adjustment, or other specific preparation conditions. Perform the necessary calculations to know the volume required and the amount of reagent to be prepared. Preparation of solution. Team 5. 1 molar tris hydrochloric acid. In a 100 ml beaker, place 60 ml of water. Put it on a hot plate with a magnetic stirrer. Add tris and stir to dissolve. Once dissolved, place a partially submerged pH measuring electrode. Measure pH. Add drop by drop of hydrochloric acid until obtaining a pH 8. Use gloves and mask. Gauge to 100 ml with water. TE buffer. In a 15 ml conical tube, place 5 ml of water and tris and EDTA. Use the vortex to mix. Gauge to 9 ml of water. 12 plates of LB agar with ampicillin. Add 250 ml of water, then add the agar. Sterilize, and finally allow to cool and add the ampicillin. Team 6. EDTA 0.5 molar. Place in a beaker 70 ml of water and add the EDTA. Place hot plate with a magnetic stirrer and adjust the pH with sodium hydroxide. Gradually add the sodium hydroxide beads and verify that the pH doesn't exceed 8. When the pH is close to 8, add liquid sodium hydroxide with a micropipette. Gauge and store in a glass jar. TBE 10X buffer. Necessary order. 1. Tris. 2. EDTA. 3. Boric acid. Place 170 ml of water in a beaker. Put a hot plate with a magnetic stirrer. Add tris and wait until it dissolves. Translucent. Add EDTA and then the boric acid. When the three are dissolved, gauge with a graduate cylinder. Store in a glass jar and sterilize. TAE 50X buffer. Add 120 ml of water to a beaker. Put a hot plate with a magnetic stirrer and add tris. Then add EDTA and once diluted it, place the glacial acetic acid. Gauge and store in a glass jar to sterilize.
Results. All of the solutions were prepared based on the calculus supervised by the professor, using the corresponding concentration formulas, verifying the homogenization of units, properly using the equipment and labeling them. Team 5 was responsible for 100 ml of trischlorhydric acid 1 molar pH 8, 9 ml of TE buffer, which was done after 10 ml of trischlorhydric acid pH 8 and 1 millimolar of EDTA, and LB culture with ampicillin. Nevertheless, the ampicillin was not added due to the time spent for the previous sterilization process in the autoclave. The calculus was done the following. For the first solution, the molecular weight was multiplied by the total volume, and that gave us the amount of grams of trischlorhydric acid to be weighed. For the second solution, C1V1 equals C2V2 formula was used to get the required volume of tris and EDTA. For the third solution, the final volume to be prepared was multiplied by the agar per plate divided over 1 liter. The same was done for LB. The amount of ampicillin was measured with C1V1 equals C2V2 formula, considering a stock of 100 micrograms over milliliter, where conversion factors were required. A general protocol to prepare any kind of solution consists of the following. First, identify the reactants and their risks, like toxicity or flammability. Then, establish the volume and the concentration you want to prepare. Take notes of the given data. Afterward, choose the corresponding concentration formula and perform the calculus. Use conversion factors if it is needed. Continue to ask or organize the lab's instrumentary. Consider different aspects of your solution like If it requires mixing, then use a vortex. If it requires heat, then use a Bunsen fire. If it needs pH to be adjusted, then get the acid and basic reactants, gloves, and the pH meter. If it requires ventilation, then work on the fume hood. If it requires to be sterile, then work on the biological safety cabinet. If it requires an antibiotic, and then add it afterwards the sterilization process. After so, you can proceed to weigh and measure. Don't forget to properly label the solution. If it requires to be sterile, then cover the top with cotton or craft paper and use a glass container with lid and consider that the volume might increase.
Team 6 was responsible of preparing 100 ml of ETA 0.5 molar pH 8, 210 ml of TBE 10X, and 210 ml TAE 50X. In the preparation of 100 ml of ETA 0.5 molar pH 8, molarity formula is used for calculating the amounts of moles present. And using this value, numbers of grams can be calculated by the formula mass equal to moles times molecular weight. For the preparation of the solution, as mentioned before, grams of ETA are dissolved in 70 ml of water with the help of the hot plate with magnetic stirrer, and pH is adjusted with sodium hydroxide beads. Of 210 ml of TBE 10X that consists of 1 molar tris, 0.9 molar boric acid, and 0.01 molar ETA. For calculating the grams of tris, boric acid, and ETA, we apply the same formulas. In the preparation of the solution, in 170 ml of water, tris is dissolved with the help of the hot plate with magnetic stirrer. Then, ETA is added and next the boric acid. After it, solution is gauged. In the preparation of 210 ml of TAE 50X that consists of 0.4 molar tris, 0.2 molar acetic acid, and 10 millimolar ETA, considering 100 ml, grams of tris, ETA, and acetic acid are calculated with previous steps, but the grams of acetic acid are multiplied by its density in order to give units of milliliters. Each value of grams and volume is added twice. For the preparation of the solution, in 120 ml of water, grams of tris are added to be dissolved in the hot plate with magnetic stirrer. Then, grams of ETA are added, and finally acetic acid is added with a graduated pipette. The solution is gauged and put in a container for sterilization.
In this laboratory session, we prepared several solutions at different concentrations that involve several types of proportions between a solid, solvent, and solution. Before engaging to the actual preparation, we had to consider substance properties such as the molecular weight, density, volume, and pH to determine the storage vessel and the measuring tools as well. Concentration can be defined as a pure proportion that exists among the components of a mixture. This measure can be useful to study phenomena like molecular interactions, stoichiometric proportions, and velocities of reaction. Molarity. This measure relates the number of moles found within a defined volume. Therefore, the amount of molecules present in a given solution can be calculated. It is useful because concentration can be expressed in consistent stoichiometric terms. Namely, even if two different solutions were added different weights of two components, they can have the same molarity, and thus the same number of particles. Normality. It is a proportion that measures the reactive capacity of the solute in a mixture. The number of equivalents is calculated from the reactive elements of a compound, using either the number of hydrogen atoms or valence, depending on the reaction that will be studied. For instance, a solution of sulfuric acid at 1 molar concentration will have a 2 normal concentration. Molality. In order to relate the effect of the solute in the solvent, the number of moles of the first compound is divided by the mass of the diluting agent. In contrast with molarity, it is a property that is not dependent on temperature, so it is useful to study colligative properties. For instance, the freezing or boiling point of a substance can be altered with the addition of an external compound. Parts per million. It is a measurement usually applied for compounds whose concentration has such a small proportion that they must be referred to within a scale of a million particles of solution. Percentage concentration. It is a representation that relates mass and volume content of a solution. It is especially useful to have a more direct preparation of solutions because the mass and volume can be measured directly. It can have three main variants: weight, volume, and volume percentage. that may be used accordingly. For instance, if you mix 250 milliliters of water with 250 milliliters of ethanol, the resulting solution will have a 480 milliliters, due to the molecular interactions between the liquids. In this case, it is more convenient to use a water volume percentage. X concentration. It is considered a factor of dilution. Several solutions are sold or prepared within a standard stock concentration, so this type of measurement is used to know the necessary volume or dilution or amount of solid that must be used to achieve a more or less concentrated solution. Consider details during solution preparation. The 10 main details that you have to be aware of when you are preparing a solution are: 1. Tariff operation. Measure the net weight of compounds without considering the storage vessel. 2nd. Micropipette tip replacement. Change the tips each time you shift from a compound or contact a different solution in order to avoid reactant contamination. 3. Liquid viscosity. Laboratory micropipettes are designed to absorb liquids with water-similar properties. If you manage a liquid with higher viscosity, your measurement may not be accurate. 4. Electrode rinsing. Remember that the pH meter electrode is stored within a potassium chloride solution. Rinse the electrode each time you take a measurement. 5. Calculation procedure. Before preparing any solution, you have to make the logical mathematical operations to determine the amount of weight or volume of each reactant. 6. pH adjustment. Some solutions require a specific pH. To achieve this, it is necessary to add the corresponding base or acid with caution to reach the exact value. 7. Volumetric flask scale. It is necessary to choose the appropriate vessel for storing accurate amounts of volume. 8. Flask size. Some solutions may be subjected to temperature or procedures, so you have to consider the possible volume or consistency changes of the solutions. 9. Labeling. After preparing any solution, for management and security reasons, it is compulsory to label it with its content, date, and concentration. 10. Using safety equipment. Laboratory reactants may be dangerous to manage because of their corrosive or flammable properties. It is mandatory to use the appropriate security equipment. Taking all these factors into consideration is a way to guarantee that all the solutions have been prepared under controlled conditions, and that are, in this way, reliable for experimental use. Otherwise, several problems may occur afterwards. Incorrect preparation of buffer solutions, for instance. Buffer solutions are used for maintaining a constant pH environment. If there's a mistake during the preparation, the pH will no longer be reliable, resulting in possible denaturation or degradation of the components of a sample. Calculation error during titration. To determine the concentration of a certain acid or base in an unknown mixture, a titrating solution with a determined concentration is prepared to find the equivalence point. If any calculation is badly performed, the supposedly determined concentrations will be mistaken as well. Excessive antibiotics. Some culture media are nurtured with certain antibiotic that will ensure the exclusive growth of a desired organism. In the case of plants, the same method can be used but with strict amounts, as excessive antibiotic concentration will result toxic to the plant extracts as well.
The realization of this practice allowed us to reinforce our skills related to the management of equipment and tools to prepare solutions properly. In the same way, the necessary calculations were carried out in order to obtain solutions of the desired concentration. This implies identifying and appropriately using the different units in which the concentrations are expressed. In the same way, through practice, we were able to recognize the proper handling of the reagents so that when preparing the solution, it retains the desired characteristics. It is important to take into account several aspects when working with the reagents in order to avoid accidents within the laboratory. Additionally, it is crucial to identify the function and the purposes of each of the solution because they are specific for each activity and the validity of the results are closely related to the correct management of said solutions and the equipment that is implied in that activity.